Today we'll be talking about how to do FFTs that don't fit inside the GPU memory. And I'm going to show you that prefetching carefully gives a big speed improvement. So the question is, what's the optimal way to compute large FFTs on a GPU? If the FFT input data doesn't fit in the GPU memory, pieces of it must be copied from host memory. And at the same time, other pieces need to be evicted from the GPU so that there's space for those pieces we just copied. CUDA provides a managed memory option that does this already. It takes pages from host memory and moves them to the GPU and evicts them back. FFT requires different data access pattern over different phases. And some of these are contiguous and other are non-contiguous but regular patterns. The problem is that when CUDA passes a page from the host memory to the GPU or back, you end up in a situation where a lot of that page isn't used. And so instead, we need to figure out ways of doing smart prefetching that can help the execution time on GPUs. In this talk, I'm going to talk about 4 subproblems. The first problem is, how do you decompose a multidimensional FFT such that pieces of it can fit on the GPU? Secondly, I'll talk about how do you parallelize the movement of data from the CPU to the GPU, the computation, and the movement back. And I'm going to do that in 2 ways, through threads and CUDA streams. Third, I'm going to talk about how we do efficient copying from the host to the device and back. And those cover batching, transposition strategies, and non-contiguous dimension finding. And finally, we build a model and we can map the parameters of the decomposition to different machines. So first, let's go over what a 3D decomposition of an FFT looks like. So here, we're going to do an FFT along the first dimension, which means this direction. So this says for all j and k, do pencils of FFT like this, all of the pencils in the x direction. So we're saying get all of the data here that is in the x direction for a specific j and k, and calculate the FFT and store it back. Then we're going to repeat for phase 2, the y direction. So do all of these pencils. And finally, for phase 3, we're going to do the z direction, all of these pencils. So as you can see, we only need to store 1 pencil in GPU memory at a time in order to decompose the problem. However, we need to get more data to and from the GPU because we want to have this done in parallel. So the first thing we can do is, let's just look at the first phase. What we can do is we can do all of these pencils in parallel, and we can break them down by threads. So the black thread is going to do part, and then the orange thread and the red thread and the yellow thread and so on are going to do each individual parts. So that's expressed by this code here. Prefetch the data, compute, and write it back. So what does that look like? We can also use streams so that when one thread is doing a copy of its data to a contiguous buffer to send to the GPU can be doing other work at the same time. So this is what a stream would look like. First, we copy the data from the non-contiguous n-dimensional array into a contiguous buffer. We do a CUDA memcopy async to send it to the GPU, possibly transpose it, do an FFT, transpose it back, copy it back, and then copy the data back from the contiguous buffer into the n-dimensional FFT. But at the same time, after we start this first one, we can do the second one. And you can see here, this CPU is only doing these parts here. So this can be done in parallel across different streams while the GPU is doing work. Also, we can have another thread do the same thing. And because the GPU is so fast at doing these pieces, it can actually finish these while these things are being done. So what we found is that 1 stream per thread doesn't provide enough asynchrony, but 2 streams per thread works optimally. And when we add more streams, it doesn't actually help the performance at all. So what this means is I can copy data from the non-contiguous buffer to a contiguous buffer, and then pass the rest off to the GPU. And then at the same time, copy another thing either to or from the GPU, back to the non-contiguous buffer or to the non-contiguous buffer. And then finally, with threads in the contiguous dimension, what we find is that after about 4 threads, you don't get any better performance. But in the non-contiguous dimension, oftentimes we have to use all of the hardware threads to get an optimal performance. And using too many threads here, as long as you don't over-provision the hardware, doesn't hurt the performance, but it doesn't help once you reach that maximal efficient number. So the problem we have here is that there's too much overhead for each data request. So I'm doing one pencil data request, and that might be a few kilobytes or so. And the overhead to send those few kilobytes from the CPU to the GPU is rather high. So the solution here is to batch these pencils up and do them all in one shot. So that looks like this. So the first thread is going to send this big batch, and the second thread will send this batch, and the third will send this, and the fourth will send this. And now the data size is large enough that we're overcoming the PCI bandwidth overhead. So what does that look like? It looks like this. So again, on phase 1, we're going to do all J, and then in the K direction here, this direction, we're going to calculate a start and stop, and then we're going to say, give me all of the indices of that section into the GPU, do a batch FFT of all of these pencils, and then send the data back in the same way. And then we can repeat this for the other dimensions. So that solves the batching problem of making sure there's enough PCI, reducing the PCI overhead. Now, the next problem is a transposition problem. So think about a 2D case. It also is the same in a 3D case, but the host memory is laid out like this. We have our y-axis and our z-axis, and the memory is contiguous along the z direction. Now, if we want to do y pencils, we're actually trying to do these pencils here, okay? So the GPU wants the data to look like this. So how do we solve this? Well, there's 3 ways we can solve it. The first way is we can transpose this on the CPU before the send. The second is we can send it just like this, but then transpose it on the GPU. And then finally, we could send it just like this and tell the CU FFT that the input data is strided. And I'll explain what that means in the next few slides. Okay, so in the first case, what we're going to do is we're going to copy data from our input to a contiguous buffer while transposing it. So that means we're going to go for each pencil. We're going to look at each value in the batch, take a single value, and then put it into the buffer transposed. So that looks like this. So we got our first row and we make that a column. And then our second row becomes the second column, and so on. Now, the next strategy is to do a strided copy with the GPU transpose. So this code looks like the following. For each value of y, we're going to do a mem copy of the size of the batch from the start to the GPU buffer. So it'll look like this. So we're going to send this piece here, then this piece, then this piece, then this piece, and so on. And then finally, we can transpose that on the GPU. The final strategy is similar to the other strategy, except what we're going to do is we're going to, again, put the data into a buffer, send it to the GPU, but CU FFT normally will do FFTs this way. What we can do is we can tell CU FFT the data is strided and say the first element is here of your FFT, but the second element is down here and the third is here, and I want you to do this many FFTs instead of saying the first element is here and contiguous and do this many FFTs. So what does this look like? Well, if we do the CPU transpose, it turns out it's about 3 times slower than just sending the data untransposed and doing it on the GPU. And it also turns out that using a strided plan doesn't really change much, and that's because most of the overhead is sending the data to the GPU, whether we tell the GPU to do it in the most efficient way of transposing it first and then having a really efficient FFT, or saying, don't worry about the transpose, just do a less efficient FFT. Both of these plans work fine because they are hidden by the latency of sending the data across the link for each of the streams. So the result is we don't do this first one, and either of these 2 strategies work well. Next, we need to talk about how we choose the dimension to send across the wire. So our constraints are that we have to solve FFT in all dimensions, and that only one of the dimensions, the last one in the C ordering, is contiguous. However, we can batch by any dimension we wish. So while the Z dimension is contiguous, we can batch by Y or X when we're trying to solve any of those different FFT pencils. So what have we found? So we found that copying a contiguous chunk is very fast. Copying a non-contiguous chunk is very slow. And copying a contiguous chunk and then striding by a certain amount, and then copying another contiguous chunk and striding by a certain amount, and so on, is fast as long as this chunk size is large enough. So what does that mean? That means in phase one, when we're doing the X direction, we're going to copy this rectangle by copying these little pieces in a batch along the Z dimension. Additionally, for the Y dimension, we're going to do the same thing. We're going to copy in a batch like this, but for the Z dimension, we simply copy this big chunk over and solve it on the GPU. What we don't do is copy Y batches in the X direction, because every single one of these axes here will be non-contiguous, whereas these axes are nice and contiguous. So here's the algorithm for finding this contiguous dimension. For the contiguous dimension, just batch by the previous dimension. Then the entire batch is contiguous and you have a big chunk. For all other dimensions, batch by the contiguous dimension, and we can copy the many contiguous pieces by using this copy data no transpose that I showed you a few slides earlier. So this is what pseudocode would look like for all dimensions for find an inner dimension. If this is contiguous, the batch dimension is the previous, else the batch dimension is contiguous. And then for all of the other dimensions, do a parallel for batch in the range of the batch dimension divided by the batch size, copy it to the GPU, process it, copy it back. So now we have the full algorithm, and we have our two parameters here, the number of batch size and the number of threads to use. Let's talk about all the parameters to the problem and how we're going to build a model to tune the parameters to a hardware. So the problem input is simply the input shape of the data. So for a 2D problem, it would be two numbers, which would be, say, 100 by 100, which means that's the size of my data. For a 3D problem, it could be 64 by 64 by 80, for example. The hardware parameters are the GPU memory size and the number of CPU cores that you have to work with. Experimentally, we're going to derive two specific patterns that are specific to the platform. One is the minimum buffer size needed to have an efficient PCI transfer. That is, if I transfer 1 byte at a time, that's not going to be efficient. If I transfer a gigabyte at a time, that'll clearly be efficient, but there's some number where if I transfer less, it's going to be less efficient, but if I transfer more, nothing changes. And then finally, we're going to find the minimum mem copy for each non-contiguous dimension stride. That is the chunk size that we need to amortize the stride misses that we're going to have later. So what is that batch size? And then finally, there are two tunable algorithm parameters. One is n batch and one is n threads. And we're going to solve these two based on all of this. So here's three different platforms. So the first platform is a workstation that I have. And I found that the minimum buffer size is 0.5 megabyte. And in 8-byte elements, which is a complex float, that's 64K elements. The GPU memory size is 6 gigabytes, and that turns out to be about 3/4 of a gig elements. The minimum mem copy per stride is 8K, and there are 8 CPU threads. And these are the numbers for Cori, which is at NERSC, and Summit, which is at Oak Ridge. So here are the tuning rules. So first of all, over-provisioning hardware threads is detrimental, but typically using all of the hardware threads is optimal. There is a lower number of threads that you can use many times, but that number is also optimal, so you might as well use as many as you can. Now let's talk about the memory. So there are 5 buffers allocated per stream. So 2 buffers hold the input and output data. 2 buffers are used for the input and the output of the GPU transpose, and 1 buffer is used internally by CU FFT, so that's 5 total. And previously, we showed that 2 streams per thread is sufficient, so that means that there are 5 buffers times 2 streams per thread, or 10 buffers per thread. So we have the following inequality to solve. The GPU memory in number of elements is greater than 10 buffers per thread times the batch size times the dimension that we're batching times the number of threads we're using. And the size of each transfer is the batch size times the dimension size, and that has to be greater than the minimum buffer size to get the PCI bandwidth. And third, the n batch for the non-contiguous batching dimensions needs to be greater than the minimum batch size for mem copy to be efficient. So on our workstation on Cori and Summit, the numbers work out like this. So 8 threads, 10 threads, 28 threads. And so what we're going to do is, first, we're going to try to solve this inequality. And if it can be solved and there is a solution, then we're going to come down here and also solve this and make sure that this can be solved too. And the minimum value for n batch is the number that we use. However, sometimes this inequality cannot be solved because the dimension size is so large. And in that case, what we do is we instead make n batch small enough so that it fits in the GPU memory. So how does the model compare to the optimal? What we did is we ran a 2D FFT size of 2 to the 28 elements, and the dimension size of the axis that I'm looking at is on the x-axis here. And we did a brute force comparison of the best parameters for each size, and then we looked at what the model would show and then compared the two. And so first I want to go in the contiguous dimension 1 here. And what you see is that for all values, the model is very, very close to the optimal, like within 5%. And you also see that as the contiguous dimension gets larger, the non-contiguous dimension gets smaller. What happens is that I can use fewer and fewer threads because there's too much data to send, and the performance falls a little bit. In the non-contiguous dimension, however, what you see is that when the contiguous size dimension gets smaller and smaller, the number of batches I can do gets smaller and smaller, and the model is not as good as the optimal because there are very few possible values, and sometimes a value that the model said for the batch size, which is larger, it turned out that a smaller batch size with more threads would be better. So now that we have a model, and the model is typically within 10% of the optimal performance, we can then try it on a bunch of different sizes. So what we see here is that if we had no computation to do whatsoever, and we got peak bandwidth, this is what the performance would look like. However, using managed memory, this is the performance that we get, which is about 3-fold off from optimal. And if we use our method, this is the performance we get, which is about 50% to twofold off from optimal. And you can see that our method is about twice as fast as CU FFT with managed memory. Similarly, on Summit and on Cori, you get similar results where the managed memory is somewhere between 4 and 8-fold worse, but our method is faster. And on Cori, we see about a 3 to 4-fold speed up, and on Summit, we see about a 2-fold speed up. So what are the conclusions of all of this? So the first conclusion is, if you have an FFT that doesn't fit on the GPU, it requires smart prefetching. And we batch multiple FFTs in a decomposition to improve PCI bandwidth. For the contiguous dimension, we batch on the previous dimension to get one large contiguous block. For non-contiguous dimensions, we batch on the contiguous dimension to get many contiguous pieces separated by a stride. For transposition, it turns out sending non-transposed data and transposing it on the GPU yielded optimal performance. And the decomposition itself has 2 parameters per dimension, the number of FFTs to batch and the number of threads. And our model maps these parameters to the compute memory and PCI bandwidth resources of a machine. And we see about a 2 to 3-fold speed up over CUDA managed memory on multiple platforms. So future work, what we'd like to do is look at, instead of trying to use the CPU to copy into a contiguous buffer and then pushing the data with CUDA memcopy async, we want to use the GPU to pull the data across the line. And we believe we'll get better performance and less tuning will be required. Second, we're building a distributed version that uses MPI so we can solve a very, very large FFT problem on a supercomputer. And third, we're packaging the implementation into a user-friendly FFT library. And finally, what we would like to do is build a distributed heterogeneous prefetch library that operates on these different shapes and phases of computation and enables these concepts that we found around batching, parallelization, strided copy, and transposition. We'd like to acknowledge the anonymous reviewers. They had a lot of great helpful suggestions. We'd like to acknowledge a person on our team, Mark Glines, for all of his comments and suggestions. We would also like to acknowledge Robert Searles and Matthew Colgrove from NVIDIA. They've done a lot of troubleshooting on the supercomputers. And this work was sponsored under a grant from the Department of Energy. And we used resources from NERSC, which is where Corey is located, and Oak Ridge, which is where Summit is located. Thank you.